This is now the second part of the EAGM presentation. So all in all, we have started some years ago several cases where we made the LCAs, as Jürgen presented before. We have now the second part. So I will not go in detail again for the cases and how we did the cases, how we did all the evaluation. Therefore, I have it at the end summary as well as some things about costs. So I will speak now about landfill construction, slope retention, retaining structures, as well as filter function. That was one of the two last cases together with the temporary road, which we have prepared within the last 5 years. So coming to landfill construction, drainage layers. Here you can see two typical pictures that are typical for landfill constructions for cappings, where we have a drainage layer, and a drainage layer is typically, if you're following the EU guidelines, is prepared in this way that you have 50 centimeters of gravel, and below and above the gravel you typically have a geotextile, below for protection for the geomembrane, and above as a filter to prevent that the drainage layer is blocked by fines from the soil above. The alternative could be you use a geosynthetic drainage layer. And you can see here on the slide the main difference, that's the thickness. And what we compared here in this case is really only the drainage layer itself. So that means we compare only the LCA impacts by the drainage material as well as the drainage core, because all the rest of the construction is the same. I have a filter above, I have a protection layer below, so we can really focus only on the main things which are different. As said, we have two cases. We had the 50 centimeter of gravel, 6032 gravel layer, and in comparison to that, we have drainage nets or drainage 3D filaments. We have taken production data, raw material data, and so on from the EAGM members which produce such products. We made an average of these, and this is then the average product, which is a geosynthetic drain in comparison to the gravel. The drainage core is a typical 500 gram per square meter material. Sometimes you have it a little bit lower, sometimes a little bit more. So as also Jürgen explained before, we tried always to look for the worst case. The estimated lifetime for the geosynthetic solution is always 100 years. We have CE rules how you can prove that these products have 100 years of lifetime. And this is the basis for all this. The material flow or the material for the calculation you can see here. We have per square meter, we have 90 kilogram of 900 kilogram of gravel. We have the geosynthetic drainage core, and similar to what we saw before in the presentations is always the same. We see that the amount which is needed to prepare and bring the material on site to install this material is heavily by machines which using much fuel and so on, and all this is in the calculation and shows the difference between the geosynthetic solution and the classic construction. Here you can see the slides as also shown by Jürgen, where we have always on the left side the classic construction, or the first column is always the classic construction, with all the things where the values come from. For example, in case of the gravel, the green line and the blue line of the installation, and where you also can see the difference in the second column with the dark column with the geosynthetic construction. So always 100%. Sorry, why it didn't work. So always the 100% column is the classic construction, and in comparison to that you can see the summary of all the different impacts, the 8 impact categories that are evaluated by the use of the geosynthetic product. And highlighted here in yellow, you can see the energy demand as well as the CO2 emissions that are not the only one, but the main impacts which we always had in mind when we evaluate these topics. So what we can see with the use of geosynthetic, we have a lower impact in all categories. except land use, because 1 square meter is 1 square meter that you have to use for a landfill. If you have a landfill capping of 30,000 square meter, we reduce the CO2 emissions by 220 tons for this site. And for example, not to forget is, we reduce also strongly the demand of natural resources, in this case, the gravel. The gravel will be used once and then it's gone. And instead of that, you can use the geosynthetic drain. The second case, which I would like to show, is the soil retaining wall. And in this case, we have these typical concrete fronts, which are built in several ways, where you have the concrete as the main part, or alternatively, you can use reinforcements with geogrids with different, not surfaces, fronts, depending on the site-specific conditions. So here you can see a sketch how the material was, or how the two cases are calculated. We have the case 4. 4A is the retaining concrete wall with a reinforced steel. Or we have the case 4B with the reinforcement with geosynthetics. Here we have calculated a long-term design strength of 14 kilonewton. This is the main product which is evaluated in all these calculations. For the calculations, we have from 3 different suppliers from the EAGM. We have values from the production, as well as where comes the raw material from, what are the typical transportation distances. Maybe this to say this in general. Always when we calculate geosynthetics, we had a long distance for getting the raw material. So in all the LCA cases, there's roughly a distance of 800 to 1,000 kilometers from the producer of the raw material, from the granular, for example, or the fibers, to the producer of the geosynthetics. And mostly we have a distance for the calculations from the producer to the site where the material is installed from 600 to 800 kilometers. In comparison to that, the classic materials like concrete, like gravel, like sand are always different, 20 to 50 kilometers, and we see this later on the last case, which I will show you. So these are the 3 products that are based for this evaluation. We averaged these data from the productions with energy demand, waste, and so on and so on. Again, here you can see the key figures for the calculations, what kind of material, how much material you use for the concrete. We always had in mind a wall height of 3 meters and then 1 meter length for the calculations to compare this. And here you can see also the outcome. Again, the first column, the left column, is always the column with the classic construction, and the second column is in comparison to that the column with the geosynthetic solution. And again, here you can see for accumulated energy demand as well as CO2 emissions, the main 3 columns, accumulated energy demand, non-renewable or renewable, in comparison to the classic constructions. Here also, as in the case before, we see that there's a really strong reduction of energy demand that is needed for the construction on site, as well as the production of the raw materials. Similar to that, we had 85% reduction of CO2 emissions. And for example, this means if I have a 3 meter height wall, 3 meter length, this reduce of accumulated energy demand is similar to what one household per year needs on energy, to make it a little bit practical. These are the 2 cases, or 2 from the first 4 cases, which we have started evaluating roughly 15 years ago. All the figures that we have evaluated 2010, 2011 were checked again in 2019, so the values and the outcome of the study is also valid today. And since 2019, we have done 2 more studies. One was shown with the temporary road by Jürgen. The other one is the filter function in a river construction, which we also evaluated in the last years. So what we did is we checked the data, what is if I have a river construction and I use instead of gravel or filter layers from sand or from gravel, if I use a geosynthetic as a filter. And here you can see On the left side, you can see this is a construction without a geosynthetic filter. On the right side, you can see it with a geosynthetic filter. Short question, it is a little bit similar to what Kent just showed. Why do we need this? If you see these three pictures, on the left side, this is roughly 50, 60 years ago. All the channels that we have here in Europe, for example, the Midland Channel is nearly 2 kilometers away from our factory. The ships are relatively small. They are move over the water in Züge, sorry. They move together, so therefore they move slow. They have more or less no waves and so on, and everything was quite good. Nothing happened on the slopes. But over the years, you have more boats that are driven by themselves. They are longer, they have stronger forces, and by that you have much more waves on these hydraulic applications, and by that you get more and more problems. And this is, for example, with the use of geosynthetic, totally different, because the fine soils cannot wash out. That's the reason why we use these materials in filter function. So if I have the classic construction, you can see it here. And the area, again, we only looked on this area where we really use the geosynthetic or the materials that we can exchange. So all the rest is not taken into account into the calculation. Here you can see the riprap or the armor stones, and then below this you have 20 centimeter in 2 layers with sand or gravel. And the alternative is to use, instead of the sand or gravel, use a geosynthetic, and then we have, depending on which area here in Europe we have different requirements and regulations for these kinds of products. For example, in some areas, typically there's a 350-gram nonwoven used as the filter. In other areas, typically it's a 750-gram nonwoven used. Both are evaluated in this study. And we had several scenarios, so we call them light short, light long, and so on. And this depends on the distances and on the weight. So lightweight is a 350-gram nonwoven, heavyweight is a 750-gram nonwoven, and then we have the distance supply for the material that is used for the alternative material. And we said, okay, it could be that you get the gravel, the sand, roughly 20 kilometers away. It could be that you have maybe 50 kilometers away. For the geosynthetics, we made a calculation based on all the data that we had from the producers of these products within the EAGM, and they evaluated what is the typical distance to a site, and based on that we came to an average distance of 795 kilometers for the geotextile to a site. Only 2 results here, so this is the base scenario where we have the light product and the short distance for the mineral layers. And with the first column, you always see the classic construction. With the second column, you always see the construction with the geosynthetic. And here are the 2 columns highlighted a little bit above and below, where you have, instead of the classic construction, the geosynthetic construction. And here you can see the reduction of CO2 emissions or accumulated energy demand are not so high as, for example, in case 3 or 4. But nevertheless, we have a reduction of all this. And you can see also for all emissions that are evaluated, you see this reduction. We have here another scenario where we have the heavyweight geotextile with 750-gram nonwoven, and where we have calculated with 50-kilometer transportation distance for the minerals. And again, here you can see the differences between the classic construction and the geosynthetic construction. As said, the differences are not so high as, for example, as with case 3 and 4, but nevertheless, there is a difference. So also here you can see we have, all in all, we have a reduction of the CO2 emissions. For all the impacts, we have a reduction between 10 to 50%, depends on the emission. We have between 12 and 26% reduction of CO2 emissions, and also for the accumulated energy demand, we have a reduction between 30 and 28%. This is what we have done as the LCA, where we evaluated the CO2 emissions, accumulated energy demand, and so on. Beside that, what we also did some years ago, we said, okay, let's start with case 1 to case 4, and let's check what is the result if we do a cost comparison. And we started this cost comparison in 2020 and 2021. And based on these, every step was evaluated. We had a consultant who did this with us. He was in contact with several construction companies, and he evaluated really the figures that are happened on site. And for this evaluation, you will see the result in a few seconds. Please have in mind that the figures that we have there, energy costs, and we speak here about costs, these are the costs from 2021. And you all possibly, hopefully, have all in mind, and if you go now to a petrol station, you see what actually happens with energy costs. And so whatever you see as a result, I think the difference will be much higher, or definitely higher, possibly much higher, as you can see it there, if we would do the same comparison today. So for the construction drainage layer, as I showed before, the differences, or the installation and what was evaluated are the following figures. So case 3.1 is a conventional construction with the site preparation. I need the material, I have to install it. Similar also for the geosynthetic solution. And if you compare these results, you can see the 100% in this case is a geosynthetic construction solution. And if you compare these with the construction costs, if you install gravel, you have 130% more costs. So the blue line is more or less the same. It's a cost for the geosynthetic construction, and the red is what is on top if you use a classic construction. And if I have in mind what Wim has told us for the MKI, there you can see the ecological costs, and you can see that there are some benefits with construction with geosynthetics. And here again, you see also another big benefit if you're using geosynthetics for the construction. I have another example that's for the case 4, for the soil retaining wall, with all the things that are evaluated. And here we have a similar result. So if you take the geosynthetic construction, we have costs of 100%. If you compare it with the classic construction, we have to add another 190% of costs. We haven't done this for case 5 and for case 6, especially for case 1, I will show you, and 2, I will show you later results. I think the difference, for example, for the case that Jürgen has shown with the temporary road will be similar. For the other case, we didn't have, for the hydraulic filtration application, we didn't have a cost calculation up to now. So to summarize what I just have shown you, with geosynthetics, with building with geosynthetics, with using geosynthetics, and I think that's really the summary of all the 6 cases, we clearly can see and show that CO2 is saved as well as other emissions when you use geosynthetics instead of classic construction materials. The differences are different. Sometimes it's less, sometimes it's more, but always you can see there is a reduction. We reduce the energy demand, and we save also natural resources. For example, the thing what Kent explained with GCLs instead of using a compacted clay liner. This is not a case which we have evaluated as EAGM, but it shows the same. You save so much natural resources, for example, the clay in this case. Beside that, we have here all the values, for example, for case 1, 2, 3, and 4. Always the green line is the energy demand and the CO2 emission for using the geosynthetic solution. And the pink line is if you use the classic constructions, you have it also here for case 5 and 6, so the filter function and the temporary road. But what we also have shown is we reduce the construction costs. So when you take always 100% as a value for the construction with geosynthetic, you can add also then something more if you use classic constructions. You can see here also the outcome for case 1 and case 2, which has presented by Jürgen. The differences are not so high, but nevertheless they are. And please have in mind, this is the evaluation from 2021. I'm pretty sure the differences will be higher today if we will do such evaluation again. So geosynthetics are part of the solution. We can reduce CO2 emissions, we can reduce accumulated energy demand. And I have heard a few months ago a sentence from somebody from the European Commission, and he said to us, the construction industry in Europe is responsible for more than 30% of the CO2 emissions in Europe. So everything what we can do here saves CO2 emissions, saves accumulated energy demand, and helps us to bring down the figures that are produced by the construction industry. Nevertheless, we also reduce the use of natural resources like clay, like gravel, like sand. Kent mentioned this example with you have to use water for prepare the compacted clay liner. What he didn't mention is you have to use fresh water. Here, especially in the Netherlands, you have many water around. You can't use this water for bringing the compacted clay liner on the right setup. You have to use fresh water. So it's not only I have to save water, I have to save really special water. And in addition, we showed you some examples how the costs are reduced by using geosynthetics on the slides before. Thank you.